Okay, so here's a problem that's important. Every student needs to be able to do it, and the nice thing is that it's not that hard, but it's extremely important. This is example 2 of section 1.7. And so we're going to use the definition of limit to prove this limit. Okay, we're going to prove that the limit as x approaches 3 of the function 4x minus 5 equals 7. Okay, so in this problem, what do we have? We have that, well, the a is 3 and the f of x is 4x minus 5. And the L is 7. Okay, so we have to prove that if absolute x minus 3, positive absolute x minus 3 is less than delta, then absolute 4x minus 5 minus 7 is less than epsilon. There's always a two-step process that we use to do this. Step 1, preliminary analysis of the problem, guessing a value for delta. So we're going to get a delta, and that's like kind of the whole thing right there. If you can get the delta, then you're home free. Let epsilon be a given positive number. We want to find a number delta such that the positive distance between x and 3 is less than delta. Okay, if the positive absolute value of x minus 3 is less than delta, then the absolute value of 4x minus 5 minus 7 is less than epsilon. Okay, so we start here with this thing, and notice how we end up. Okay, we work with it a bit, but the goal is to end up with that thing, okay, that absolute x minus 3. Okay, so working with the conclusion of the conditional, we say, okay, we have this. Okay, we've got this right here, and we're going to try to produce something that looks like this, and you'll see the benefit of that in a moment. Okay, well, obviously you can simplify the expression on the inside of the absolute value bars. That's 4x minus 12. That happens to factor to 4 times the quantity x minus 3. By the way, it's not a big news flash that factorization is able to happen. After all, the people that make the problem, the Stewart people, they're, kind of pre-cooking the problem so that this x minus 3 comes out of it. Well, 4 is a positive factor of the expression on the inside. It can be pulled outside the absolute value bars, and we end up with 4 times the absolute value of x minus 3. And so here's the key thing. Here's something about delta. Okay. Something about epsilon. Here's something, but it's also something about delta. Here's something about epsilon, and just by working with it, okay, we didn't, bring in anything from the outside, we end up being able to say something about delta. Okay? Because if we can say something about absolute x minus 3, we're able to say something about delta from this inequality over here. And so, in other words, we want delta such that if positive absolute x minus 3 is less than delta, then this expression here, which is the same thing as that expression that we had, the f of x with the f of x in it, that is less than epsilon. Well, we can do that. That is, if positive absolute x minus 3 is less than delta, then divide both sides by 4. Absolute x minus 3 is less than epsilon over 4. This suggests that we should choose delta equals epsilon over 4. So that was the first goal that we had, right? Was to find a good delta. And we're just going to say, okay, let's pick a delta epsilon over 4. So whatever epsilon is, well, we're just going to divide it by 4, and then we're going to be able to achieve for every epsilon there exists a delta. Of course, we remember the original f of x was linear with coefficient of x of 4, and that just ends up being what we divide epsilon by. And we, could have seen that in advance. Okay. Right. F of x was 4x minus 5. F of x was 4x minus 5. Well, at the very beginning, we knew that we were going to take that 4 and say that the delta is just going to be epsilon over 4. So step 1 is always find a delta, and step 2 is to state the proof showing that this works. Okay? So we always have to say, given epsilon positive, choose delta equals epsilon over 4. Okay, that's the part that we got from step 1. Now here, it's kind of like we say the same thing every time because we are providing a proof which is according to the definition of limit. So, okay, so now here we're going to say this part. If positive absolute x minus 3 less than delta, then what can we say? Well, we get this string of expressions which are all the same, except there is one inequality there, which of course we need, because we need to be able always to conclude something is less than epsilon. Well, that's what this says. Okay, so f of x minus L, f of x minus L, which can be written as absolute value of, which can be written as absolute 4x minus 12, which can be written, since you can do the factoring, as 4 times the absolute value of x minus 3, is less than 4 delta. Okay, because this inequality is true, this inequality is true. I mean, it's still going to be true if you multiply both sides of this one by 4. But we are taking delta to be epsilon over 4. And so absolute f of x minus L, which is absolute 4x minus 5 minus 7, is less than epsilon. And that's what we were supposed to show in the definition. Okay, that's what we were supposed to do. Now, this string, might look familiar. Remember how we arrived at the delta originally, okay? Originally, we had this line. Okay, I should put quotes around this because this is, one of the lines on the previous slides. That's how we reasoned to our delta, because we saw, this here, and so if that thing's going to be less than epsilon, divide both sides by 4, and the absolute x minus 3 is going to be less than epsilon over 4, and putting epsilon over 4 for delta will make this proof go. And so it just went, didn't it? Okay, we were able to say all of this, and so we're going to be able to say that we have this limit that we were supposed to prove. Okay, so to summarize, if positive absolute x minus 3 is less than delta, then absolute f of x minus L less than epsilon. And so again, by the definition of the limit, we are able to say that we do have this limit. It is true that the limit as x approaches 3 of 4x minus 5 is 7. That's what we were trying to accomplish. And so we're done at this point. Okay, we have proven it. We don't need a picture. Okay, we're done. QED. Okay, we've got this proof. But now here's kind of a check. What's going on in the geometry. This example is illustrated in figure 9. Okay, so here's f of x, and it's within epsilon of 7 if x is within delta of 3. So it's good to state somewhere what we're actually doing here. If we're proving a limit, not finding a limit using a graph, but we're actually proving that a limit it's a two-step method. Okay? Step 1 is a preliminary analysis of the problem, guessing a value for delta. It's not much guesswork there. I mean, in this problem anyway, the delta that we got was very straightforward in a step-by-step, found in a step-by-step way. Delta must be a function of epsilon, right? So delta was epsilon over 4. Delta is a function of epsilon. And then the proof showing that this works, which is, in a way, it's trivial, because if you get the right delta, then it's going to work. It's just a matter of stating it in a way that is acceptable if you're going to try to say that you've proven something. And so that right there is a good case to study for the problem that you're going to have to do many times of proving a limit.